Alabama. And the fifth speaker is Mamin, who is the founder of LunCo. All right. So yeah, I'll be asking. So this is going to be the ethics of the panel discussion. Each speaker we have, I'll be throwing, let me say, a general question, and then I'll be asking some questions that are actually relating to our field of expertise, So now the first question, which is a general question, and that question actually goes to Dr. Moll. Okay, Dr. Moll. So I would love to ask you, how can emerging engineering techniques reduce mission costs while improving sustainability for long-term lunar and planetary missions relating to your field? So how can emerging engineering techniques reduce mission costs while improving sustainability for long-term lunar and planetary missions? So thank you. Just for 2 minutes. Thank you, sir.
All right. Just making sure the question is directed to me, right?
Yes, directed to
Yes.
you.
All right. So as you know, like I am in the educational sector, and we have many panelists here who are making some out of this world things, which is very cool to learn from through this wonderful convention. From the educational side of view, what we do is we work on things which are mostly TRL1 or TRL2, which is technology readiness level 1 or 2, which are basically concepts on paper, trying to run through the math and physics and trying to see like if something comes up through that. So in that pursuit, I have had the fortune to work on different technologies related to Mars as well as Moon. And then related to the Moon, I have been working along with AFRL folks, Air Force Research Lab. So those folks, what they have been investigating are this low thrust trajectories. So in the future, what we want to do is like, as you know, to place anything to space, it takes a lot of money. So even 1 kilogram, you need just tons of money to just place that 1 kilogram. And for making humans to go to space, it involves just too much money. So you want to minimize this cost in some way or the other. One way to address it is using advanced propulsion systems. And for that, people have been looking at these new propulsion systems, including electric propulsion, which are cleaner to the environment, as well as they provide benefits from cost point of view. So I have been investigating these trajectories, which are extremely complicated because they take very long time to go around the moon and do their operations. So they involve larger timeline for transfers as well as for operations. So that itself is a big challenge. And then if we can address that, then we are moving towards at least some more advanced propulsion, at least in the cargo missions, if not human missions. So that has been one of the things that I've been very closely working, and I can tell you, again, like that is one of the many things that people have been investigating, in, at least in my side of the world. And then another thing that people are trying to advance is like how close you can land to the place of interest. So it's basically pinpoint landing, whether it be on the moon or on the Mars. So for that, at NASA, I'm very close to NASA Marshall Space Flight Center and NASA Johnson as well. So folks are working on different aspects of it, and they are trying to work on something called human lander system, which wants to place humans as close as possible to their post, wherever they have to land near the south pole of moon. So that has been ongoing. So those are some of the things that I can tell you from my experience and from what I learn around. But other panelists can tell much better from the startup point of view or like the company point of view.
Wow, thank you so much, Dr. Mo. That's an innovative one at your hand. Thank you so much. So I'll be asking Merrick to actually answer the question relating to his own field of expertise. How can emerging engineering techniques reduce mission costs while improving sustainability for long-term lunar and planetary missions? Thank you. Over to you, Merrick.
Yeah, thanks. there's so many areas to go to. So you could either talk about engineering tools and engineering methods, or you can talk about new technologies that are helping us do new things in space, right? So I think which path would you like to go down? Because I want to make sure that I speak properly to the audience.
Please come again.
Sure. Can everybody hear me well enough? First of all, I guess I'll just speak to methodologies. So there's always new pieces of software and code that runs faster, that lets more analysis happen, that puts power more in the hands of engineers to make trades. But I think one big one is space systems are complicated, right? Space systems comprise mechanical engineers, software engineers, electrical engineers, and that's just on the design side. And then when you have to go build a system, you have to design for building. And I think one big emergent technology is the ability to say, when a engineer makes a design decision early on in the technology readiness level part of the phase of designing a space mission, all the way up to when you're making a production, what's the feedback loop? And I think modern technologies with better databases and access to the cloud of information. Let me give an example. If an engineer makes a design decision that requires something to exist in the real world, the question is, does the supply chain exist such that that thing can be used? And if an engineer chooses, let's say, for example, an NVIDIA chip as part of their processing unit, but there's none available or it's too expensive, just that one decision has a real world impact on, does the company have enough money to buy an NVIDIA chip or however many they're going to buy? And are those chips going to be available? So I think that's probably a very large impact. And how does a decision that is made at any place along the chain impact everybody else? And very good companies are successful that are able to handle that impact. And companies that aren't able to handle that impact don't do well. And so often you have executives or leaders making decisions, and then you have engineers making decisions. And those two things don't always align, or people don't understand the impact of it. So the emerging technologies that allow that information to span all interested parties is probably one of the most impactful things that we can do to have efficient systems that can become reality. Because at the end of the day, you don't want logistics to break. There's electrical engineers who know how to build great electrical systems, and there's mechanical engineers who know how to build great mechanical systems. But it's when you're actually trying to pragmatically make it real, that's where companies fail and succeed.
Oh, thank you so much, Merck, for that good contribution. So because we are trying to keep up with the time, so let me just move further to the next person to actually answer the question. So I'll be calling on Rina Fiber, which should be representing the CEO of LunCo, that's Rob Mami. Rina Fiber is the COO of LunCo Health. So Rina, please, I would like to ask you, based on your own expertise, how can emerging engineering techniques reduce mission costs while improving sustainability for long-term lunar and planetary missions? Thank you.
So first of all, I have to say that it's Rod Mamin, founder and CEO of LunCo. I'm just from Rina's account. So hey, everyone. At LunCo, our actually goal is to reduce those costs, and we are tackling that from several perspectives. The previous speaker said, we're actually developing a comprehensive simulator that is focused on novel methods to design space missions. And we build it in an open source manner, meaning that accessibility, it's a huge deal because, like, a significant portion of costs comes from the software. And in our case, we have several methods how to provide high quality software thanks to AI that allows actually to at least start developing systems at much lower cost. And That's one way. Actually, nowadays the world is built on open source software, and we strongly believe that open source approach would make a huge deal. Of course, a huge question is how to make it profitable, but thankfully, if you work on a global scale, you can get a decent cash flow, allowing you to build that software and provide core functionality for free. Also, in our case, we are heavily inspired by the ideas that are coming from blockchain. You know that actually nowadays, because of tons of reasons, and it's not just because of the compliance, but often the engineering happens, as people love to say, in silos, meaning that it's often the case when teams all over the world, they have to reinvent the wheel. And often it happens not because of the compliance, but because of the complexity, because of the complexity of the systems, because of lack of communications. And having like a universal ledger with all the designs that are indexed by AI, that is a solution that would allow actually humanity on a global scale to reuse existing solutions. So we're also working on such a ledger that would allow like everyone to submit their designs into that global system, and then again everyone to reuse their results to search through those results with the AI. And we're heavily relying on Web3 technologies, meaning that it also allows pretty everyone in the world, no matter where they are, to actually make those contributions and even make that profitable, meaning that anyone in the world, no matter where they are located, can benefit from it. So to summarize, in our case at LunCo, we are aiming to address the problem from three perspectives: high quality open source software instead of like SDK, our software, Web3, and Web3 to share designs and AI-based engineering when AI index tons of data and share that data with everyone. So thank you. Back to you guys.
All right, thank you. That was a great contribution from.
May I ask a question?
Yeah.
Since
all
this
right.
is a panel discussion, if I may, hopefully this adds and helps.
Yes.
I would love to hear a little bit from the previous speaker on the idea of intellectual property. I fully appreciate that you want to build systems out of things that are open source for everybody, but I'd love to hear a little bit more about how that conflicts with people who are building systems wanting to develop their own intellectual property, and maybe how you're able to help those groups who do have something that they can't share because those companies are trying to become profitable, and what thoughts have been put around there. And if we don't have time for that question, that's perfectly fine, but I'm super interested.
So that's a great question, and maybe that's one of the main questions. First of all, I have to say that I'm a systems engineer, but my background, I'm coming from open source software. And the thing is that in open source, there are many approaches that kind of tackling the same issue. So we are talking about lowering the cost of space missions, and often actually it's profitable for there are cases, let's say like that, there are cases when it makes sense to develop something together. So for example, developing standards or like, I don't know, like communication standards, standards for lunar rovers. If your company profits from manufacturing rovers or manufacturing unique, I don't know, sensors, by working together on things like buses or things like that could be reusable, it makes sense just to collaborate. So you still have that intellectual property, really high level, really unique. You leave it up to you. But things that make sense to do together, you do together. That's what often happens with the software. So for example, nowadays, modern world is run on Linux. And the thing is that it's like a common infrastructure, and there are tons of companies who use Linux, who make profits from Linux. like literally all the servers, they run on Linux. And for those companies, they make profit somewhere else, and they contribute to common infrastructure. So open source, often it's about finding those common infrastructure. That one way. Also, another example, for example, Raspberry Pi. It's a hardware, and it's fully open source. The thing is that, and you can manufacture Raspberry Pi by yourself, but it would cost, you can buy it for like $80 or something like that. But if you're gonna do it by yourself, it would cost you like $3, $4, several $1,000s, and they profit from overall ecosystem. So, and that's applicable to space as well. So there are cases, again, like it's not applicable to every case, but there are cases where you can profit from growing the infrastructure by open sourcing some standards, some approaches. You make more people use it, and you can sell those manufactured pieces. And it would make sense because, you know, like if there is like a demand for, I don't know, 20, 30, 50, 100 unique computers. Yeah. Okay.
Yeah. All right.
Happy to get connected on LinkedIn and discuss it privately. I'll drop my name in chat.
Okay. All right. Thank you so much. Thank you. Okay, so I'll be asking Rama on how emerging engineering techniques reduce mission costs while improving sustainability for long-term lunar and planetary mission, relating to your field of expertise as the head of AIV at Space Inventor. Thank you.
Yeah, thank you for that. I think some of the things are already touched upon by the previous speakers in terms of engineering tools or the standardization. They are all the key as we move forward, because if two systems cannot talk to each other effectively, there is no system working as a satellite or space system. Now, moving forward, we think of building bigger structures, bigger systems, space stations, or establishments in the space. So it's very important that we address this aspect of building the tool. The major, like as you see in any space system project lifecycle, the majority of the cost is spent while physically building the structure or while physically working on the system, assembling, integrating, and verifying it. So, and this is not something happens independently without the systems or the initial system designs in place. It should happen as an integrated approach, starting from the concept all the way up to realization. It should be an integrated approach. Now, to make it integrated, today we have access to plenty of tools, but there are a lot of challenges today because we end up using multiple islands or different types of tools, and they struggle to talk to each other. So this is the common challenge across the space organizations today, like systems, when it comes to systems or when it comes to assembly or when it comes to simulation. So there is a need to integrate all of these tools together and also to standardize these processes and the way we do things, engineering methodologies. So that is the need for our, and because there are plenty of academicians here, one thing we all need to know, also think about is how we can reduce this timeline of AIV into smaller, how we can simulate a lot. So today, for example, we do simulations before we build a hardware, but simulation has its own challenges in terms of the precisions or in terms of assumptions. There are a lot of uncertainties. How we can make it closer to the hardware so that we don't need to look for a model to test the simulations, or we can trust the simulations, how we can use them, and so that it's more like a digital twin wherein you don't even need to think about, once you have it in the simulation, and when moving one step forward, even can you do some simulated tests and see that, okay, this would be the results of the system if I do the test. And if you can compare the results very closely, then for the second product, you don't need to even test it because you can just integrate it and launch it. That could be the moving forward, because we have access to a lot of tools today, but we have our own limitations. So these are some of the things I think we need to look into from practical aspects of building a spacecraft or space systems, how we can make them more modular, and how we can use them more standardization across. And for example, between the systems, in terms of connectors, there may be plenty of different interfaces between the systems. Now, how can we standardize them? How can we use for example, we have, when we connect the phones today, we have a common USB-C type charger, which is very common across. Can we do something similar in the space systems wherein you don't, or even let's say, think one step ahead, let's make every system wireless. Can we think of those kind of scenarios wherein the modularity and integrating and assembling and launching becomes easier? So that duration is reduced, means it is a lot of cost saving for the project, because if you see the project life cycle, the majority of the cost is spent in building and testing the systems. So I think if those things are addressed, that will be a bit much more beneficial, and a lot of cost could be saved moving forward. So that would be my few thoughts.
All right. Thank you so much. Thank you so much. Thanks so much, Rama, for your contribution. All right. So I'll be asking to close the general question. Now we still have the questions that still targeted to each speaker based on their own expertise. But to close general question, I would love to ask Dr. Amoloye, how can emerging engineering technique reduce mission costs while improving sustainability for long-term lunar and planetary missions, coming from the aerodynamic perspective, sir?
Okay, thank you very much. I actually want to come in from the materials perspective. That is the development of more radiation resilient architecture. As you know, spacecraft, while in space, they are exposed to a lot of cosmic radiation. And so if the emerging technology now that allows for the development of more radiation resistant materials, when those are used, those materials will allow for the space systems to last longer in space and be not degrade as easily as the previous kind of materials. And so when that happens, it ensures that there is the need for replacement, in-orbit replacement, or the need for taking to replace things that have degraded from Earth will be not as much. So that overall will increase will reduce the cost of our space mission, and also make sure that the mission takes longer before there's a need to replace them. That's what I have.
Thank you so much, Dr. Amoloye, for your contribution coming from the material perspective that we need to have materials that are radiation resistant. So moving on to the personal question for each speakers, I would like to ask Rama, and based from the background you're coming from, being an AIV expert, and you are into the space system industry. So I would love to ask, what engineering trade-offs must be made when balancing spacecraft performance with environmental responsibility and mission reliability? What trade-off made? Okay, now let me give you an instance. Let's say when designing a new spacecraft, you are constantly fighting between raw power, keeping the mission reliable, and being more environmental conscious. When you have to choose, what's usually the first thing to get sacrificed in that trade-off, and why? Do you get my question?
So I think what you are trying to ask is basically some trade-offs which needs to be considered while designing a system in terms of sustainability and their mission objective. So how do we do a trade-off?
Yes.
Okay, so it's a very interesting question. And again, I would say that I think sometimes what we do when we do a design is like, for example, how do we start a spacecraft design or a space mission design is with a set of requirements. So we need to study something, or we have a top level objective to achieve some specific objectives. And based on that, we start describing the requirements. So we define, okay, to meet these objectives, this is the kind of platform we need, this is the kind of orbit we need, and this is the kind of mission we need. And based on that requirements, we further break it down to subsystem levels or unit levels, and we say that to meet this overall objective, this is the kind of systems we need. And further, we define, okay, to build these kind of systems, these are the components we need, these are all the specifications of those components, etc., etc., and it goes down further, lower and lower. This is how the requirements flows down. Now, when defining the requirements, what normally is done is sometimes there are margins. And because we think that space is an area where we cannot do any more corrections, and this is only one launch, and we need to do it perfectly and more reliably and more more rugged, we end up defining stricter and stricter requirements, and those requirements flow down. For example, in the so far we have been thinking of doing engineering model, qualification model, flight models. So we had different types of model philosophy. Before we actually launch a satellite, we would have done a couple of models in ground and tested them and qualified them. Now today we know that we need not do that because a lot of data is already available, and we can directly do it at a stretch with the support from a lot of tools available, which would give us the same result as we actually do it on the ground. So that saves us a lot of time. With the new space kind of concepts in place, we know that we can do that, and that works. Now, second part is about the level or the specification margins, what I was talking about. So far, if you see the historically, we have been building systems with radiation hardened or radius space grade components. Now we know that we did not, at that time, that was the need because the launch vehicles were very few in number, and we once launched, we didn't have access to launch frequently, and we had to do once in 4 years or once in 10 years or whatever the life cycle it used to take. But today it is not the case. We can launch anytime, the launches are happening more frequently, so we have easy access to space, and the cost to reach or cost to access space has reduced considerably. So we really need not, and today there are plenty of companies who are using the COTS, commercially off the shelf components, slightly upgrading or additional testing to the space and launching, and still successful and operationally working for many years and keep repeatedly replenishing the systems in space. So these kind of hot processes are needed in today's scenario, and they need further to be improvised. For example, today we started thinking of, okay, now we are launching so many satellites. Now we have plenty of satellites in space which are debris. Now how do we remove them? Now for those to address those things, we started thinking from the design itself. Okay, if we need to make these kind of commercial new space sustainable, we need to have some methodologies in the system design which takes care of the satellite once the mission life is over. For example, maybe you deorbit it, or you push it to another orbit, or there are methodologies. Now these are the kind of things we need to implement in the design stage itself, so we know that okay, it is sustainable. And I think the system, everyone is constantly working towards it. I think there is some more efforts needs to be put in that. And again, you would see today there are plenty of companies working on how can we clean the space, how can we launch a satellite and clean multiple satellites together, or how can you refuel the satellite so that it doesn't become debris. So these are some of the things we need to take care in the design stage itself, so that it doesn't impact, or it is sustainable. I hope I answered your question, but I'm happy to add anything if I missed.
Yes, yes, you answered so well. Thank you so much for that
Thank
question.
you.
And I believe that the participants are able to understand what he has actually said. So without wasting much of our time, I'll actually want to call on Rina, and I would love to ask him this question, which is directed to him. As commercial lunar and deep space mission increase, what innovation in rover design, flight mechanisms, and radiation mitigation are most critical for mission success? I'll come again. As commercial lunar and deep space mission increase, what innovations in rover design, flight mechanisms, and radiation mitigation are most critical for mission success? Coming from LunCo. So I'll love you to take that question. Thank you, Rina. Just 2 minutes, please. Thank you.
I'm sorry, could you please repeat the question? Had some issues.
All right. Okay. So as commercial lunar and deep space mission increase, what innovations in rover design, flight mechanisms, and radiation mitigation are most critical for mission success?
It's an interesting question. I think, frankly speaking, it's not about specifically robot design. It's about human systems, and it's about being able to deliver those robot systems. Because, you know, like coordination, it's really hard. And AI, obviously, AI assisted, I'd say like that, AI assisted tools that allows us, you know, like to deal like easier with the requirements management, to exchange information much more efficiently and faster, and coordinate on a global scale. So I think it's not so about robot design, it's more of human systems design that allows less people to exchange information faster and control those robots faster. So it's more of a coordination at the human level rather than just pure robotic technologies. And of course, batteries. Like it's all about energy, it's all about batteries. So batteries and more efficient human systems.
All right. So we talked about coordination and also more efficient human systems and all. So the next speaker that I'll be calling for this panel discussion is Dr. Amoloye. Coming from the academic perspective, how can universities and national agencies collaborate to accelerate the development of robust, scalable space system for cislunar economy? I'll come again. How can universities and national agencies collaborate to accelerate the development of robust and scalable space systems for cislunar economy? Thank you, sir.
Okay, thank you very much. That's a very important question. I think the best way to go about that is for national agencies, universities, and startups to form something that is called a public-private academic partnership. With that, the national agencies, for instance, like the Space Agency in Abuja for Nigeria, can develop some kind of roadmap or some kind of mission, a national mission in space technology, for instance. And then universities, then the national agency would also try to make funds available for research and development towards those set mission goals. And then universities can key into that kind of mission by gearing their research towards the problems that will naturally come from trying to fulfill that mission. Universities are better poised to do the background research, the high-risk research in fulfilling the missions, and then they will get funding from what the national agencies make available in research grants. When the results from those kind of R&D from universities, the high-risk R&D from universities, which are published, then startups can try to work on prototyping the results from the R&D, and then so the cycle goes, and then the mission set by the national agency can thus be fulfilled. National agencies as well as startups can also provide spaces for internship opportunities for students in universities, where, of course, the students in universities will be exposed to multidisciplinary studies at the university level. But then when they have spaces to go in the startups and, of course, at the national agency level to try to have some experience in the specific missions that have been set out by the national agency. And also the national agency as well as the startups can also provide spaces where researchers from university can go on sabbatical and try to bring, after sometimes, after the time spent on sabbatical in those spaces, they can bring back the experience to the university and try to also disperse that in educating the students who will naturally also be tutored towards fulfilling the mission goal that has been set by the national agency. So a kind of partnership that involves all the stakeholders is a way to go about it. I hope I have answered your question.
Yes, thank you so much, sir. Yes, you rightfully answered the question. Talking on public-private partnership, and also like getting lecturers and faculties to go for sabbatical leave to ensure that they have more knowledge that they can actually help in their research. So thank you so much, sir. And I'll be calling on Merrick now to ask. Now, Merrick, you being the CEO of and the co-founder of Radiation Team, and that's coming from the business perspective, how can startups and national agencies collaborate to accelerate development of robots, scalable space system for cislunar economy? I'll come again. How can startups and national agency collaborate to accelerate the development of robust, scalable space system for cislunar economy? All right, over to you, Merrick.
Gosh, that's a really hard question, and the real answer is I don't know. You know, what the radiation team does is assist many companies, both academic, commercial, and government, make systems that are more robust and resilient to surviving in space against ionizing radiation, whether it's at the material level or the IC level, the component level. So we're not really in the business of building systems and collaborating with institutions to get funding, whether it's SBIRs and you know, in the U.S. Funding from U.S. Government and corporations to build systems. So I don't actually, unfortunately, have a whole lot to say to add value to that. But I would like to go back to the other conversation, the gentleman who talked about robust systems in space, because I think I can add a lot of value to that, and I think it will also kind of maybe hit how startups can actually get started in a way that helps them, which I think is also the spirit of the question, if I may. So yes, we if that's okay. So companies are learning that they can build systems out of commercial electronics, which is great. The problem is that they have to know how to do that right. If you build a space system out of the electronics that are made up of your TV and your toy robot and in your iPhone and of your car, you know, automotive grade electronics, and you launch it, you can certainly build it, and the system can get on a launch vehicle and it can be launched and it can power on and it can start to do something. The question is it going to survive its mission, whatever that is? Some missions are very, very short. They're simply looking to power on and send a signal back, and And then the VC or whoever, or the small company gets to say, great, that was success. Let's go launch a second one. As the previous speaker said, it's cheaper to launch things. So people don't have to do one mission. They can do multiple missions for the same cost or a lower cost and iterate and learn from that. The question is are they taking the right risk posture to launch? And so, for example, you could buy space grade parts, and this is a very cartoon picture. It's not fully true, but you could build your system out of space grade parts, and you could launch it and it would be expensive. Or you could build your system out of commercial electronics and it would be much cheaper, but it might die. So you have to spend a certain amount of resources, time and engineering money to say, if I'm going to build it out of these commercial electronics, is it going to survive? And if in doing the testing and the analysis, if you end up spending more money proving that the commercial parts are going to be robust than if you would have just built it out of the space system, well, then you should have just started with the space system because you ended up spending more resources than necessary. And so many commercial companies that come for our help, they come and they say, Merrick, what should our radiation reliability be? And the answer is, I don't know. What's your business model? Like, how much money do you have? Some companies have lots of money and no time and they have to get it up. Other companies have lots of time and no money. And some companies don't have either and they're just trying to succeed. And so it's a question of what is the risk posture of the company, and are they willing to try to launch on a coin flip, saying they're happy for a 50-50 chance because it's a demo mission, or James Webb Telescope better have worked the first time because there's no second chance. And the Starlink satellites needed to work to a certain threshold, but it was at some point just better to launch it and see how they did because the second wave is coming and you can learn from it. So every company, depending on what they're doing, has to assess their own internal risk posture. And when you're a private small company and you're the CFO or the CEO, or you're just even an engineer who's trying to help the company succeed, you have to say, I'm designing a system, and when am I going to stop? Because the system is good enough and it's good enough to launch, even though it's not perfect. And every company has to make the decision of whether they want 99.99999% reliability or 80% reliability or 75% reliability or doing a Hail Mary. And every business model is different. And so when a company asks us, what should our radiation reliability be? We help them figure out what that is based off of their company's constraints and budget and schedule and engineering talent. I might say the best solution is in software, but they don't have any software engineers. They only have electrical engineers. So then we go solve the problem in electrical engineering or vice versa. And so it's a fine line that companies have to draw and they have to figure out, because the engineering problem ends up becoming a business level decision for success. So I'm sorry I didn't answer the proposed question, but I felt like I had important value to add there, where it's not the same for every company, and every company has a personal decision to make about how they're going to try to succeed in the commercial world.
All right. Thank you so much, Lee. Thank you so much for contributing to what the other speaker said, and for the fact that you're able to give an insight about the question being raised from here. So I'll be asking Dr. Just give me a second, please. I'll be asking Dr. Moll, being in the AI perspective and you being an expertise, how can national agencies adopt AI to accelerate the development of robust and scalable space systems in the research space?
Thank you again for the question. And I was actually raising my hand to say on the same thing. Actually, Professor Amoloye, if I'm saying his name properly, so he actually covered all the things that were in my mind from the educational side of things. But just to add, some examples that I've seen, because luckily I took all my education from Neil Armstrong's Institute, where there have been almost 30 astronauts and even more are lining up. So many of them went to the moon, and there are moonwalkers there actually. So they started, Purdue University started this cislunar initiative. So that is exactly geared towards this thing where you have institutions like Purdue University itself. Then there are these startups, or there are these other companies who are making different parts for the Artemis mission. And then there are agencies like NASA, or there are other governmental agencies which are forming the policy. So all of them come together. I have had the fortune to take education from some of these people. One of them was an expert in, he's an expert in space policy. So he has been there at third topmost position at NASA, and also CEO of AIAA at his time. But now he is a professor there in space policy. Then there is another professor who is very popular, Professor Howell. So she works on trajectory design, which is very useful again for these kind of lunar missions. Then there is a third professor who works on debris. So all these different professors are working on different kind of problems that are confronting these lunar missions. But then they are coming up with, along with the government, to change this high level, strategies to specific challenges, like what needs to be done, and then what capabilities need to be built. So again, many of the things are on paper or worked out through some physics or math. But then to execute them, we need the help of these companies who are making it. So that's where everyone has to have a common roadmap, and they should not be going in different directions, but in the same direction. Adding another example from my current university where I'm at as an assistant professor. So here, luckily, I'm very close to, again, a NASA Marshall Space Flight Center. So we have something called Alabama Space Grant Consortium. So all these different states have their own money that they get from the government, and that is used for expanding space efforts, especially for these lunar missions which are upcoming. So what it is helping me and people here at my university is we have some very nice talents, some very nice PhD or master's students, especially for PhD students. We have this fellowship through which they can actually study and work on these problems which are related to these actual world challenges. And then that also helps us to prepare this talent to be used in future for these organizations. So instead of doing some other random research project, they are actually working on these real world projects. And these kind of fellowships pay for almost all of their education. And on top of it, I use half of my funds to support them for their stipend. So that keeps them motivated enough. And then in 3-4 years, they come out with a product which is actually helping these agencies solve their problems. So these are the two examples that I've seen in person. So thank you.
All right. Thank you so much. Thank you so much, Dr. Moll. Thank you. Thank you for that wonderful contribution. So yeah, this is the end of the first panel discussion. So to Dr. Taofiq, Amoloye, to Rina, Fiber, Dr. Moll, Rama, Merek, thank you for sharing your articulate perspective, and this section was very, very informative. And I believe that we can now move forward with greater clarity for every participant here on the call. So please join me as we give them a virtual applause for this incredible section. So let's just give them a virtual applause just for 30 seconds, just to celebrate them. Yes, thank you.
Thank you.
Thank you so much.
Thank you so much.
All right, okay. I can see someone actually raising hand on the call. So I'll have to ask and call the person on the call. Omotola Okiwale, please, do you have any question? And to whom are you directing it to? Thank you.
No, sir, I don't have a question. Thank you.
All right, okay. All right. All right, so now there's a new development. You'll be joining the panel, second panel and the third panel discussion together, just to ensure that we're able to close on time. And I believe that there are some of us in different time zones that are actually getting close to the 90 in Nigeria. We are just 6 minutes past 7 p.m. So we'll be joining these two panel discussions together. And on this section, we'll be having Neal as one of our speakers. We'll be having Rafael, we'll be having Dr. Dhara. So Neal is the founding CEO of Titan Space Industries in the United States. Rafael is the director of Stardust Consulting in Spain. And Dr. Dhara I've actually called her, and she was not actually that was able to give us a demo presentation. Who is actually who is an educator. So yeah, I would love to ask us this general question. The same ethics actually applies to the panel discussion we have in the first panel discussion. So I'll be asking a general question and also a personalized question to each speaker, and for each general question is going to be for 2 minutes, while the question directed to each individuals will be for 3 minutes. So please just keep to time. So this panel discussion will be focusing on space economy, policy, infrastructure, governance for a multiplayer era. And here we're talking about space laws, regulatory frameworks, commercial space architecture, space planes, access, and in space infrastructure and collaboration. Now, I would love to ask this general question. As space becomes more commercial, what economic model will best ensure safe, accessible, and scalable space transportation and operations? I'll say that again. As space becomes more commercial, what economic models will best ensure safe, accessible, and scalable space transportation and operations? So I'll call on Rafael to talk on that. So Rafael, the floor is yours. Thank you.
Perfectly. Thanks again I am very happy to be here. It's a very interesting question because obviously commerce in space is a new frontier. The space agency, they are more involved in space exploration, return to the moon. But now for more commercial things in the area, we can develop a cislunar space. This is the Earth orbit, the moon orbit, and the lines of communication between them. A lot of companies, private companies, have a lot of opportunities to develop commercial opportunities to give support to the official missions. When we're talking about these commercial opportunities, we are talking about lunar landers, we are talking about constellation around the moon, around the Earth, for give service to a lot of people, for more and more possibilities. It's a new world. They are billions of dollars that they are companies looking for, and these are real economic development. The question is that following the international law, all these companies are under the control of his state, that they are the international liability in case of conflict or accident. For this, to have more commercial opportunity, it's very important that a lot of countries have national regulations according to the international regulation. For this, give free commerce in the space. But this is very important because of the final, to develop this, they need investment, and the investment follow the legal framework. It's very important to have all these steps for go ahead.
All right. So thank you so much. Thank you so much for that contribution, Rafael. So I will also be directing the same question to Neal. As space becomes more commercial, what economic models will best ensure safe, accessible, and scalable space transportation and operations? So Neal, the floor is yours. Thank you. Neal, are you on the call? Okay, he's not on the call. All right. Maybe just the network. All right, so I'll be calling on Dr. Dhara.
Sorry, again. Listen, thank you.
All right, that's what
as I presented 2 days ago, cislunar economy is going to remain a major dream if you keep on working on rockets. So I have 2 minutes to explain. Let me talk fast. Okay. Jeff Bezos said let's do huge highway to space. Elon Musk says, I want to build huge rockets that take hundreds of people, 100 people per flight, and 50,000, 100,000 tons, metric ton to Mars. But not gonna work. Rockets are not the future. So this is where we come in. We are building the cislunar transportation infrastructure. Everything else is A, a dream, if not B, bullshit. You cannot do this stuff at scale with present technology. And present technology is vertical rocket launch. You can do everything with rockets like we're doing now, but at small scale. When you talk about economies of scale, when you talk about trillion-dollar economies, cislunar economy, not gonna happen with rockets. So unless we start acting like we are at Titan Space, not gonna happen. You can dream along, but there has to be a paradigm shift in space transportation technology, systems, infrastructure, and there has to be a paradigm shift, a seismic shift in terms of people's thinking. The industry is married with vertical launch rockets. Not gonna happen with that. That's my answer, Okijesu.
All right, thank you so much, Lee. Thank you for rounding up the first section. So we moved on to we moved on to second section, and I directed a question to you while you were not on the call. So this section is actually
Or was I ranting without?
Can you hear me?
Hello?
Hello, can you hear me? I can hear you from here. Please,
did you people hear me or not?
Hear me?
I was talking for 3-4 minutes.
Yes, we can hear you all along.
Yes.
Okay.
Please just give a thumbs up if you can hear me from my end. All right.
Yeah, we can hear you. You can continue.
Yes, I was trying to reach out to Mr. Neal that we could actually hear him from our own end. So maybe he's going to come up again. All right. So I would love to direct the same question to Dr.
I can't hear
Dhara.
you people. I don't know what's going on. I can't see anyone. I don't know whether you all hear me speak for 3 minutes.
We can hear you. We can hear you. We are. Can you see our reactions?
Okay.
We can hear you. We can hear you, sir. We can hear you. You can continue.
All right. So, Dr. Dhara, as space becomes more commercial, what economic model will best ensure safe, accessible, and scalable space transportation and operations? So, Dr. Dhara, the floor is yours. Thank you.
Yeah. Thank you. It's really indeed an interesting topic that you have asked me. So talking as in the field of entrepreneurship, so I will say a very simple answer for it or model for it. Two types of model that I can see. One is a service based, one is a product based. Now, as we know, as Neal has said that we can see the future as to marry to a rocket that is not just a small prototype. That's, I really agree to it. Adding to some of the points, space tourism is going to be one of the key area that researchers and scientists, they're working along with the astronauts. So this is one of the key, just like an operation you said. So it is going to be act as a service. Product is going to be a space tourism that is going to be very active in current days. Next is that, as we know, everyone is looking towards sustainable environment, sustainable technology. So soon we have to be adaptable towards solar system and other renewable systems. So one of the biggest source we can get it from solar cell, solar energy, that is going to be also be active in the coming generations, also as a service and a product. And the third one, very trending the space debris. Both is going to work as an service and a product. So I would like to highlight these three areas. It's going to be rapidly increasing on this area in terms of services and also hands on hand with this space economy. Yeah.
All right. Thank you so much, Dr. Dhara. Thank you for that awesome contribution. I would love to ask, is Neal still on the call? Before moving on to the personalized questions that they targeted to every.
Yes, I am here.
All right. Okay, so let me ask you the same question. As space becomes more commercial, what economic model will best ensure safe, accessible, and scalable space transportation and operations?
Didn't I just answer it?
Hello?
Okay, Kijutsu, didn't I just answer that?
Okay, you actually mentioned what we actually discussed in the first panel discussion when you're talking about cislunar economy. So that was what you mentioned. Maybe you answered that when we could not actually hear you because we could not hear you on the call initially.
Okay. Well, look. Safe, accessible, and scalable space transportation and operations. That's what you're asking now?
Yes.
Yeah, same story. You can do anything nice and cute little stuff like we are doing now already at small scale. When you say scalable space transportation, how will you do that with rockets? Elon Musk is trying to solve that problem with his Starship, which is awesome and powerful and beautiful, but it's not going to work for its intended purposes. I've written analysis on that. You can access it on my LinkedIn newsletter. So it's of no use talking about that solution when we still have the problem. Without solving that problem with another dramatic, revolutionary even system, you will keep on having the same problem. It will be same shit, different pile. Excuse my French. So you cannot solve this problem easily. It has to be completely different. The architecture has to be different. The flight trajectory, the flight path, the commercial approach has to be completely different. It's not anymore a matter of evolution. Okay, we have a rocket here, and now that rocket has to be bigger, and the rocket has to be a bit more advanced, this and that. Not gonna work. That would be evolution. You cannot work with that system and infrastructure any longer for large scale. I'm not talking about small scale. Large scale. You have to have a different method. You will not put your child on a rocket, right, for launch. On the other side, we're talking about, hey, we will have kids in the space in the future. How then? Well, we're working on that solution. But unless you do that, there's no other solution. If it were, I will be working on it, right? That would be tens of billions of dollars in it on annual revenue, but there isn't. So that's why we have this multi-vehicle cislunar transportation infrastructure that is end-to-end, from Earth surface to the lunar surface. Only then can you do it at scale. As a matter of fact, I am the inventor of that system with that problem in mind. So we worked backwards from lunar surface to Earth surface, and we came up with this multi-vehicle transportation infrastructure. But otherwise, I don't know. Maybe there are some brilliant people who know better than I, who have great solutions, but it cannot be done. For example, Elon Musk, brilliant guy. But he is saying, you know what? We're going to launch with a Starship, which is like a skyscraper. We're going to launch from Earth's surface. Then we're going to have a separation. The booster comes back, as you know, and the Starship orbiter will orbit on Leo. Then it will be refueled 10, maybe 20 times. Have to be visited by tankers, that one orbiter. It has then to have all the fuel, and then it will go, for example, to the moon orbit, dock with Gateway, and all that kind of silly solutions. It's not going to work. And then they want, they want to have a Starship landing on the moon. Not going to happen. Never. They're working on it. They got $3 billion from NASA. And not going to work. Not going to happen. Despite the $3 billion that NASA thrown at them. Why? Because of the design. It is an inherently flawed design. So even the brilliant Elon Musk and the powerful SpaceX will not be able to solve that problem. Why not? Because they still are working on vertical rocket launch technology. It's a ballistic missile, people. So I hope that answers your question, okay, KJ. Jesu.
Yes. Thank you so much, Neal. Yes, well answered. Thank you. So,
Thank you.
Yeah, I'll be directing the next question to Rafael. Being an expert advisory service in legal practice and regulatory affairs and space and aerospace management projects, I want to ask you this question. How can nations harmonize international space laws with the rapid space of commercial space innovation and private space station infrastructure development? I'll say that again. How can nations harmonize international space law with the rapid pace of commercial space innovation and private space station or infrastructure development? The floor is yours, Rafael.
Yes. This is one of the most important way at this moment, because normally for the harmonization, we can use the United Nations system, FUNOSA, COPUOS, and we have the international space law treaties, but they are from the Cold War. They are a lot of things that we can use at this moment, but they are others. The Outer Space Treaty gives to the states the opportunity to make national law, but at the final, we need to make this harmonization. The natural way to do this is in the United Nations, but due to geographical problems, geopolitical problems actually in the Earth, we can see that today there are two blocks. One of them is Artemis blocks that they make a refuse of the more of the legal parts of the international treaties, and by another hand, the International Lunar Research Station from China and Russia, they are made more or less the same, including the possibility to create this legal question. With this, we have the evidence that the states need to have something of harmonization, but they don't agree to make all together. I was meeting with people from the United States, with China, with different countries, and by the moment this is very difficult. But for commercial activities, should be better that these go in the same line. And also for question about the space debris, space traffic management, the use of natural resources in the space, go to the moon and using the cislunar space, show interest in the disharmonization, because if we don't have this harmonization, probably each state use his better national law, make a something like a forum shopping for what is the best, what is the cheaper, what is the national regulation without the obligation of insurance, for example. I believe should be very important to have this harmonization, because at the final should be a problem. In my previous intervention, I was talking about that in the European Union, it's not possible to make harmonization using the Lisbon Treaty. And for this reason, the European Union say, okay, we can talking about harmonization of space law, we make harmonization of the market using some regulation. It's like a truck for go ahead and advance, because without a global situation should be more difficult to give more opportunities for commercial activities. I believe we can afford put more commitment in the COPUOS, and the evidence that all the states are in intention to collaborate. They are these two examples, Artemis and Neal Earth. They are between two. They are around 70, 18 countries with intention to create a new space law that included new things like use of natural resources in space, security, etc., etc. They are the intention, but this is so difficult at this moment due to the geopolitical situation. But we need to working hard for go in the same line.
All right. Thank you so much, Rafael, for that incredible contribution on how we can actually harmonize space laws. So I would love to call on Lee. I think Lee just joined the call. And Lee, so we were talking on space laws. We were talking on how space economy, policies, infrastructural, and governance for a multiplayer era. That's actually the focus for this conversation. So because you are one of the speakers here, and I believe that there's something that you, from your professional background and years of experience in the military, also serving as the vice president for the SpaceX under mission and launch, and you also having ThinkOrbital and all as the founder. So I want to ask this question from you. What partnership between government and military or commercial operators are essential for sustainable orbital infrastructure and space domain awareness? So I'll ask that question again. What partnership between government, military, and commercial operators are essential for sustainable orbital infrastructure and space domain awareness? So the floor is yours, Lee.
Well, thanks very much. And again, I apologize. There was a little bit of a mix-up on the time. But in any case, it's a great question, and it's a very important question because, as we know, space is what we call the 3 Cs. It's contested, it's congested, and there's competition in outer space. So we have to be very, very careful as we kind of forge ahead. We do joint operations in outer space. And I think a big piece of this is, number one, respecting international treaties and international law. There's kind of standards and practices that we like to maintain. I think debris mitigation is an excellent example of that. There's not necessarily a law for debris mitigation, but there certainly are standard practices. And maintaining a joint catalog of all of the space objects is absolutely critical as we get more congested in outer space, right? So we, have on the order of 30 to 40,000 items that we track in outer space. The International Space Station has to do multiple maneuvers, to avoid space debris and things like that. And the situation is not getting any worse. And, I look at space debris kind of like I look at global warming. We all recognize that there is a problem with global warming. However, no one is really doing a whole heck of a lot about it. And that's a problem. and I think that you have a very similar problem with space debris, right? We all recognize that space debris is an issue, yet there's very little money or emphasis being placed on cleaning up several of the useful orbits. So I think we owe it to humanity to be better stewards of outer space and ensure that our laws and standard practices are followed.
All right, thank you so much for that. So I'll also love to ask you, Lee. There's a question from Umbong at the chat box. He says that I think powering a spacecraft with fusion reactors is better than normal fuel. How true is that from your level of experience and all? Thank you. Do you get the question, Lee?
Lee, just kindly unmute. Yeah.
Yeah, I did not hear the question, unfortunately. Yeah, I was trying to find the question in the chat, but I don't see it.
And after Lee, after Lee, I would like to comment also briefly.
Neal, why don't you start out? How's that?
Sorry.
No problem, Lee.
Why don't you start out, Neal, and I'll
thanks, Lee. Appreciate. So listen, first of all, nuclear power propulsion is at the moment in the pipeline, but it's still a pipe dream for now. Of course, we have a lot of R&D to do. We have committed. One of our branches, Titans Works, is named after Skunk Works and the Phantom Works, where we will do R&D investments, including nuclear propulsion and power. But it's not as easy as just deciding to do that. We don't have the technology to, let's say, miniaturize the technology in order to make it happen. And then there is the nuclear thermal propulsion and the nuclear electric propulsion trade-off, or a hybrid. So if you go to my newsletter on LinkedIn, you'll see that last year we've done 2, 3, 4 analysis on the trade-offs of nuclear thermal propulsion and nuclear electric propulsion. That was last year, 12, 14 months ago. So you'll see a few analysis. And back then we were saying we are going for nuclear electric propulsion, while the whole world, including NASA, was saying nuclear thermal propulsion. And now we're saying we may work on a hybrid solution. But it's an amazing question, by the way, Udom. Props to you, but it's not as easy as just deciding that. Chemical propulsion, for the intended purposes, cislunar will work fine. So we as an organization are saying, to be safe, we will use chemical propulsion for cislunar transportation and traffic, and we will invest heavily in nuclear propulsion for Mars, which is 2032 and beyond, or for our second generation spaceships. So to be safe, we're saying we're not going to use it, for cislunar, and especially not for the time being, maybe in next generation. When you want to go to Mars, you will need nuclear propulsion. Then again, Starship with chemical propulsion will be a death trap for people. Okay, I hope that answers the question. Lee, please take it over.
I'm going to vehemently disagree with you on Starship being a death trap for people there, Neal.
Okay.
Falcon 9, took us
but
several
Falcon 9
years.
is a different technology. It has nothing to do with Starship technology.
I think it's not the technology, Neal. It's the people that are working the technology and their ability to test it.
I don't agree. Okay.
I understand. Can I state my case here?
An entirely different technology, but yeah, please, I'll stay shut. I'll stay quiet.
Yeah, I don't think the technology is all that different. We're using chemical propulsion. We're using something that is truly understood from a chemical propulsion perspective.
It's nothing to do with rocket engines. Also not. It has to do with the design and the technology. But anyway, I'm not gonna.
I thought you were going to stay quiet, Neal.
Yeah, I will.
I don't think you can.
Apologies.
Only one thing. I work usually with people involved in launchers, and for me they are different things. One thing is going to the orbit, to the Earth, but at this moment, with the technical of this moment, we need chemical rockets because they are not alternative. Another thing is, for go to the moon, go to the Mars, we can use and develop nuclear system, but for takeoff for the Earth, by the moment they are not possibilities with nuclear, including if they are in the future nuclear engines, for the risks and accident, probably people say, no, for go to the orbit using chemical rockets, and after that you arrive on orbital station in the low orbit, use nuclear for going to another. If they are a problem, should be in the space, not over Florida or over Kourou or something like this. I believe it should be the best balance of if you are another system for go to the space, is perfect. But by the moment, I believe all the people is thinking in chemical, better, worse, but chemical for to arrive orbit, and nuclear for go faster in the space, because we need to go faster for radiation and for saving time, because if we need to spend months of years to explore in solar system, we remain in here. We need to go faster and working in weeks, not in months or years.
Thanks for getting us back on topic, Rafael. I appreciate that.
All right. So, that was an awesome engaging section from there. All right, so I'll moving on to ask Dr. Dhara. That's going to be the last question for tonight. And I would love to ask her, coming from the education perspective, how can emerging technologies like AI, machine learning, miniature satellites, low-cost testing platform empower students and young engineers to participate in global space innovation? I'll ask that question again. How can emerging technologies such as AI, machine learning, miniature satellites, low-cost testing platform empower young students and young engineers to participate in global space innovation? Thank you.
Yeah. So excellent question. And I will say this is one of the very trending topics that you have said. So one is that machine learning. So entire engineering system or advanced engineering system is completely relying on machine learning, artificial intelligence, digital twinning, and many more we are going to see. So which is tying up with this robotics engineering, which we can also say as an unmanned aerial vehicle or robotics. So these are the core area. Now, how this can really improve it, this machine learning itself is the answer. It itself is an innovation. It itself is an algorithm which develops a replica of something, which develops a replica or creating a digital twinning of something. Suppose we have one space capsule over here. So using the coding, using the data set, using the algorithm, using the historical data, we can make a replica of that. And we can reduce the cost of manufacturing. So this is one of the biggest impact that innovation can bring. Second impact, the educational sector, it is booming. The R&D, it is helping or assisting all the scientists to boost up, to collaborate, and bring out some effective outcome so that the industries can implement. It can be a pinch, maybe a 1%, 1.2%, or the impact, but it can bring a this 1.2% of small impact in some small component, it can bring a revolution in the ecosystem of the complete product. So AI has a very good hold on this. This is one of the innovation. Now, connectivity between using AI, connectivity between the software and the hardware. Again, it's another biggest challenge, but nowadays it's a very trending. For an example, I think currently this is again already is existing. For an example, we have an UAV, right? We are keeping this UAV for an border patrolling system. So in that system, from the ground control station, I can able to monitor everything. An alarm is buzzing if any anormal activity is happening. So all this is happening based on AI. AI play a very, very vital role. So how we can enhance this? So as an educator, first, I will say as a project-based, mission-driven collaboration not only within the country, but also exchanging the ideas and the knowledge transfer. Maybe India can have certain excellence in this research. Other US can have something. So we can exchange ideas to develop something great for the nation, great for the international domain or growth of the economy of both the countries. So this is one. Growing this hub and spoke economical growth in innovation centers or the entrepreneurship centers, irrespective of any country, stamp of any country. So if we are doing or registering the IPR, whether it's a copyright, patent, right? So I think these are the certain areas that we can focus more into it, as these are the few of the, I think, points I have said as point of educator, right? So I think I have given some bit of picture how we can improvise it. Yeah.
All right. Thank you so much, Dr. Dhara, for that great contribution. So I will, coming to the end of the panel discussion, I just want the speakers to just say one or two things. Maybe there are still some ideas or something to talk about. Maybe what you missed while talking about when I asked you the questions, like the personalized questions. So I just want to give you 1 minute just to share your points again, or maybe you want to elaborate on it or just emphasize on what you said in the past, or maybe a new idea. So please, just a minute for anyone.
Okay, so if I may correct one thing, or at least address one thing. So Lee just said about the fantastic people at SpaceX. I don't disagree. They are great. But you cannot say, okay, this neurosurgeon can also cure cancer. It's a wholly different specialism. Okay, it's a rocket. It has rocket engines, but F9, Falcon 9, Falcon Heavy are proven technology improvements. Starship is a wholly different animal. Anyone who says, oh, it's the same, you're not fooling me. You're not fooling the people, right? So it's not the same. Starship is an entirely different design. It has to have hot staging, for example, because they thought they were doing it right in the first try. Then they figured out, no shit, we have to get hot staging, which was invented by the Russians, I think, 50 years ago, if not 1,000 years ago. So no, they don't know everything. And of course, they test and they iterate, but the inherent design flaws of vehicles like the Starship are not going to help revolutionize as we are talking about now. We're not talking about, oh, let's keep on doing the same stuff over and over again. Otherwise, we wouldn't have this discussion. This is about the future. So yes, I am still, and I have written lengthy analysis on this topic. I'm not just, talking out of my neck. I have the proof behind this on paper. So check out my newsletter. But to say, okay, because they are SpaceX, they can do it, and also Mars, and also with chemical propulsion. Why is it a death trap? Last 30 seconds. It's a death trap because you cannot return to Earth unless you have local ISRU. And you cannot have local ISRU, which means fuel production, if you have a complete system that cannot be done with robots or remotely. So that's why it's a death trap if you are counting on chemical propulsion. The whole industry is wondering why Musk is still working on chemical propulsion starships for Mars. A lunar orbit, okay, that's great. But Mars, chemical propulsion, return, impossible. It's just not going to happen. Okay, thanks.
Neal, I admire your passion. I think you're dead wrong, but I admire your passion.
I think you're dead wrong, and I admire your passion also. Thank you.
First of all, there is plans for in situ propellant production on Mars, so please do your homework there. And
of course there is. I say at scale. You cannot do anything at scale, man. Come on. Okay, I'm not going to discuss anymore. Thank you.
Okay. No, I really appreciate the fact that you're going to bet against SpaceX and Elon Musk, which has proven to be a bad bet for many, many years. So best of luck with that. I want to thank everyone.
I'm not betting anything. Who say so? I'm just saying they're doing wrong. Okay? And Starship has nothing proven. It hasn't proven anything. You can put rocket engines on a pig and a pig will fly. So anyway, we are not going to agree on this.
That's great, Neal. That's why we have these wonderful forums for discussion. I really appreciate everyone's time, and let's all do our homework. Take care.
All right. Thank you, Lee. Thank you. So is there anyone that have anything to say? Just in a minute before we just round up with this conversation. Okay, Dr. Dhara.
Yeah.
All right.
So first of all, I'm really very happy to be a part of this panel discussion. So I learned a lot of things from Neal and Lee, then Rafael sir, the policies and all. So yeah, that's what I will say. There are a lot to learn from each other's thing. Yeah, I've learned a lot, and in future I would like to learn further with them as well. Yeah, thank you.
Yes, for me, an opinion is very interesting, the discussion about, because it's so different, the system to go to the moon with Artemis program and the China's program. China's program is following more or less the Apollo system, and the architecture of Artemis is so complicated to arrive with the SLS to the moon, with the Orion capsule, with Artemis, with the Gateway space, with the lunar lander, with 2 options. It's more complicated. Probably in the next year, we can develop all these things that we can talk in before. And by another hand, this is talking about official missions. And another question should be when private companies go to the moon using his system, SpaceX, Blue Origin, China's, India, Europe, go to the space, we have more opportunities to have technology, regulations, and what should be the future and humanity. Probably in the next few years, we have amazing discoveries about this, and probably we have more opportunities to discuss what should be the better system in technical, legal, and economical system. Thank you.
Right. Okay. Thank you. So I would love to ask any of our participants that actually want to talk, aside from our speakers, maybe you have something to say just for the convention rather. So please just go on.
Can I talk?
Yes, doctor, you can talk, Dr. Amoloye. Yes, sir.
Okay, thank you very much. I just want to express my appreciation to MARVECX and his team for the invitation to participate in this convention. It's been so amazing and it's been very interesting. And what's more interesting is the fact that MARVECX, that is Marvelous Ainde, Okiki Jesu, Francis Dedeji, and so many more are products of Kwasu Aeroastro. So that's a testament to what we can do when we think we can do something. So thank you so much. I really look forward to the next edition.
Thank you so much, Dr. Amoloye. Thank you for such an encouraging word, and thank you so much, sir. I really appreciate. So is there anyone else before we close the second panel discussion and the third one, which is the last one?
Can I say something? Okay, Kejesu?
Yes, you can. You just in a minute.
Yeah.
Thank you. So
I want to also thank the organization. You guys did a great job. This was my first time participating. But I also want to thank the attendance over the last 4 days. You know, I will close with saying, you know, Formula One fans, great people, you know, tennis fans, sports fans, great people. But space enthusiasts have two defining aspects. One is they want to help benefit humanity. And the second is they want to help inspire other people. And this is amazing. This is a community. The space community is different from any other community. And this is what I want to thank the community for and the organization. And I will look forward to participating next year. Thank you.
Thank you so much, Neal. Thank you, thank you, thank you. All right, is there anyone else? Your final words?
Can I chime in real quick?
Yes, please, Dr. Moll.
Yes, again, I would say thank you very much for including me among all these wonderful people. And it's always an excuse, you know, you have to find some excuse to learn new things. And it's very hard for you to just, you know, out of your whatever, like lab room or your classroom, you have to come out and learn new things. So thank you for organizing this, because that helps me learn from so many awesome individuals who are on the screen. So yeah, looking forward to anything that happens in the future. And great job in organizing this amazing convention. Thank you.
All right, thank you, Dr. Moll. Okay, Samuel, just a minute. Yeah, you can come on.
All right, yeah, I was gonna say that thank you guys so much for organizing this program. This is my first day actually staying all through to the end. I've actually attended sometime, but not all through to the end. And I must say that I learned so much from Neal, from Lee. I was so amazed at what Lee has been doing, and from Dr. Dhara. Yeah, that was really beautiful. I mean, the space education. And here, Dr. Moll, actually, I sent you a message on LinkedIn. I've been following you for a while now. And yeah, I've quite learned a few things from you. And thank you so much. And yes, to Dr. Amoloye as well. It's so beautiful. Thank you so much for the things that you do and the wealth of experience that you all actually have shared for us. We are so grateful. Thank you very much.
All right. Thank you, Samuel. Thank you. Thank you. All right. Is there anyone else? Okay, our participants are saying thank you so much for Amri's Ari saying thank you so much for the organizers and speakers for your inspiring work. I'm truly motivated and excited about the future of space and its community. All right, that's from Zahari. So let me read another from Ayobami Additional said, can you share the Google form again? Okay, this is actually a request. And from Tripati, he says that as a space enthusiast, I'm grateful to participate in this event. Thanks to all the speakers. These are from the participants on the call. And from Amoloye, she said that, okay, well done, everyone. Thanks to all the speakers and panelists. So thanks to moderator, you're just fantastic. So thank you so much. I really appreciate you. So thank you to all our speakers for this second panel discussion, to Neal, to Rafael, to Dr. Dhara. What a great discussion. gave us valuable and practical and engaging things to talk about and think about, such as the fusion reactor or the normal force powering spacecraft. Thank you so much. Thank you so much, Neal. Thank you. And I pray God actually bless you. So yeah, so I'll be handing over to Marvelous to give the closing remarks. So thank you so much. Yeah.
Yeah, thank you all for joining the convention from day 1 to day 2 to day. Thank you all for joining. We are so grateful. We are so grateful. Thank you, Mr. Lee, for joining the call. Thank you, and Mr. Rosen for joining the call. Thank you, Dr. Moore, for joining the call. Thank you, Dr. Dhara, for joining the call. Thank you, Dr. Amoloye, our own lecturer. Thank you for joining the call. Thank you, and Rama, for joining the call. Thank you, and Mamin, for joining the call. Thank you, all our speakers. We are really grateful. We are really grateful for joining the call. Thank you, all our participants from day 1, with different times. So we have some people that are joining that the current time zone from the young end is around 2 a.m. Like Dr. Dhara now, the time is around 12 a.m., which means the time has already gone. So thank you for joining the call. Thank you for sacrificing your time. Thank you for sacrificing your space for this moment. Thank you for sacrificing your work for this moment. Thank you. We really appreciate that. We really appreciate that. I also want to appreciate my team in terms of Okiki Jesu that moderates for us today, in terms of Princess Aria that she was actively in the chat section, in terms of Adesina Obami, he was also actively in chat section, in terms of Joshua Igbunu, in terms of Francis Adedeji, all of them. I'm really happy for all of you for supporting this vision. Thank you for joining us. And once again, we really love you all. We really love you. Thank you, thank you, thank you, thank you. And also, we have a request for you, because most of us, we are graduates, we are all graduates. All of us, it's only one of us that is a computer scientist. All of us are aerospace engineers. So we are looking forward to advance our academics. So we will be glad to have any support in advancing our academics so that we're able to establish and expand this vision, to the global level. Thank you for joining the call once again. And yeah, thank you. I'll hand over to our to the moderator, Okiki Jason. Thank you once again for joining the career. I appreciate that. Thank you.
All right. So before we get to go, I want us to just have a virtual screenshot, like a virtual photograph. So I would love us to put on our videos and we just take a screen photograph. So yeah, let's do that. So Marvelous, please kindly do that from my end. Thank you.
Hey. Okay, let me see if I can try. I'm coming. I don't know if anyone of the team can try it from their end, because I'm trying to see if I can try from my own end.
All right, let me see if I can try from here. Okay. All right. Just hold on, please. Okay. I think we are good. Yes, we are good.
Thank you so much.
Thank you.
Okay, see you next year.
Yes, thank you, Neal. Yeah, bye. Yeah, bye,
Mr.
everyone.
Rafael, we appreciate you. Mr. Rafael, thank you for being with us. Mr. Rafael has been with us since day 1 of RPC. In 2023, in 2024, Mr. Rafael will be with us. And also Dr. Aishwarya also has been with us since last year. So we really appreciate your time. Thank you, thank you, thank you, thank you. I appreciate Dr. Amoloye. We appreciate you, sir. Thank you, sir. Thanks, sir. Dr. Moore.
Thank you so much. See you next year. Thank you.
See you next year. Yeah. I love you all. Thank you.